In the model builder, under component 1, click Turbine Flow, SST. In the setting window for Turbine Flow SST, look at the physical models. So we have the physical model. The physical model of the compressibility, choose compressible flow Mach under 0.3. The background flow is now set to be fully compressible. This results in the density to vary separately. Okay, the effective non-constant background density are included in the linearized Navier-Stokes equation too. The importance of including this depends on specific application. The effect of inserting the compressible flow, it depends on application. We go to urban flow and choose symmetry. In the setting window for symmetry, we choose symmetry. Okay, this is for symmetric boundary condition. Here, in the physics, choose outlet. For the outlet, we choose (19) only. We have here also the inlet. Choose 3 only. In the setting here for inlet, we put the boundary condition for inlet. So we have the velocity by the boundary condition. We can change the velocity. Yeah, first we say that this is a fully developed flow, and then the fully developed flow by U average here, average velocity. We put UN from parameters. Okay. So it's a fully developed turbulent flow profile at an inlet. So we're gonna generate the mesh. In the setting for mesh, we will type, this is the mesh for safety, because we will have also the mesh for acoustics. First we will have a free quad here. It's a free tetrahedrons with or option free quad. For the free quad, we select inlet and outlet only. Change the size. In the element size here, from the calculation, let's choose fluid dynamics, and we will put it extremely fine. It depends on your capabilities. We can put it as fine, extremely fine. Okay, so we'll go to general size. We also element size. In the element size, so choose for fluid dynamics and click custom. This is a custom for every element in the domain. So we put the maximum value to be 0.05, and we put the minimum value to be 0.1, and the gross to be 1.1, and in the curvature factor text field we type 0.4, and the resolution for the NARB region we put 1. sweep here. So we're gonna see how he do that for the inlet and outlet port, the free quad. And then for the sway is a swept. In the setting window for swept, the domain selection, and 100-meter level choose domain. We will put some domain as swept values from this domain. We will choose one domain and two only. They will be swifted in the same number of elements. And then we gonna see the distribution, how we distribute that in that axis. So we choose domain 1 only in the distribution, and then we type 8 here for number of elements in the distribution. For the second one, we'll have another distribution here. It's for the second one, and we will type we will leave it as 5, and then we build all. You can see how these things like distributed like that. From mesh here, in the domain selection, we're gonna choose domain and choose the third domain. Also we put the distribution in the distribution and choose predefined. Number of elements will be 15, and we type 4 for element growth. We have this reverse, like becomes so much smaller here, but it's big here. And then we have sweep 3. The sweeps in the setting window, we select domain, and then we select domain 6 only. It's 5, 6. We're gonna make a distribution for it. In the distribution we type 8 here. After that we're gonna have another sweep. We're gonna choose domain. In the main domain we select 5. And then we put a distribution. The distribution will be predefined. Also to have 15 parts with an element ratio and with a reverse direction. Build all. Okay, for the free quad, then we have corner refinements for walls. Locate the boundary selection, and then from the selection select walls only. Build all, and then we go to make free tetrahedron in the inner port. Then we choose size select boundary, choose 26, which is here, and the element size, custom, and then maximum element size will be 0015. Then we make a boundary layer. We have the geometric entity selection, and then we choose wall. And in the thickness adjustment factor, we will type 1.4, and then we have built out. It's going to make this mesh as tetrahedron and make the boundary layer mesh. You can see here, this is how it looks like. It's more fine here in the boundaries and more fine here as we put as a condition, and for boundary layer also you can find how it's very fine on the boundaries, and it's okay any other else. Now we're gonna go to the study. So this study, we will type study 1 and for CFD. In the study settings, we remove general default plots. Step 2 in the stationary study expression. In the study expression, select the auxiliary sweep and then plus add. We are making two studies, 0.05 and 0.1. From the run containing for list, we're gonna make class parameter. So the results in 0.1 will depend on the results on 0.05. After he solves in 0.05, he will give the results as initial for 0.1. In the study, show default solver. Know that the solving will take 5 hours per value for the Mach number, and then we start to make compute. We have here the progress. It's 5%. It's for we still stationary. You can see conversions here, nonlinear conversions, and GCRO-DR. For nonlinear conversions, this is the percent convergency, and for GCRO, this is the percent of convergency. And this is number of iterations. And then he starts to solve the 0.05 Mach number. I think it will take some time for solving these values. This is step 1. He assembling the matrix. we have two plots, velocity and pressure, and turbulence variable, as we have k epsilon, k omega SST. He began to solve linear system, where the first matrix is for the first step for 0.05 Mach. After he solved the first step, he began to make segregated solver the velocity and pressure and turbulence value with iteration numbers. After completing the study, we go to the results and how it will be demonstrated. In the result toolbar, click 3D plot group. In the setting for 3D plot group, type CFD velocity, and then from CFD plot, choose volume and choose transparency. The volume for demonstrating all the volume in this section, and the transparency just for showing the streamlines of the flow. On CFD velocity, again, choose streamlines. In the streamlines section, in the streamline position, number 50, for increasing the streamlines, and select the boundary 12 here, and 26 here. We're gonna select them, click on select all, and then remove. We need only 12 and 26. So we have 12 here, yes, and 26. Okay. After selecting 12 and 26, click to expand the inner style. Here in style. And then we're gonna change plot to volume 1. Right click on streamline and choose color expression. And the CFD plot, click plot. We can see here they changing the color to a velocity color. After completing the CFD velocity demonstration, we're gonna have another demonstration, turbulent viscosity. So we're gonna 3D group again, and here we're gonna write CFD turbulent viscosity. Turbulence, we're gonna do that on a surface. So we have surface. In the setting for surface, look at the expression tool, the expression here. Okay. In the expression, we're gonna put the expression of turbulence, which is PF dot MUT capital. So we're gonna plot. We can see now the turbulent viscosity. Then we have turbulent viscosity plot. So first, from the results, we add 1D plot group. From the 1D plot group, we're gonna write the name CFD turbulent viscosity axial. Plot that in the center of our shape. So we're gonna have like a line here to the center. Dataset, and then click line 3D. X will be 0, Y will be minus 0.001, and Z set to minus 1 for the first point. And the second point, X also 0, Y is 0, Y is 0.1, and then Z is 1. So we go to plot. So you can see this is inside the pipe. We go to the turbine viscosity axial in the 1D. In the data set, we locate the line we just made it, and then in the title, we choose from automatic to label. We can write the title, or he will have a label here to put it here. From CFD turbine viscosity line group, we choose line graph. In the line graph, in the y-axis data, we plot turbine viscosity SPF dot MUT. He will make it the unit Pascal second. And then the X data, from the parameter list, we choose expression. And in the expression, we type Z. So he will do the turbine viscosity with Z. In the Ligand section, in the automatic here, we choose manual. Here, we write Mach number equal 0.05, and then Mach number equal 0.1. And then blot. You're gonna see the blot here. Yeah, and how turbine viscosity changes much in the region of the resonator. And then after it ends our demonstration of results of CFD. So we will go to the mapping, multiphysics, and acoustics.